wonderful program. And I'd like to welcome Matt Nunes, who's at Lancaster University, and he's going to be talking about analysis of network time series.
All right, thanks, Guy. So thanks for all of you who came up early this morning. This is a light start to the day. It's more about getting across to you the concept of what's going on and how we're going to attempt to analyze these network time series problems in general. As a general method which will probably have many applications and many different avenues of research. And this is joint work with Guy Nason over there and Marina Knight, who should be in the audience. There we are. And really this is born out of some early work a couple of years ago that we did with the government security sort of problems. And so it's really about network time series. And what do I mean by a network time series? I mean data which is observed on a network, which is a collection of nodes with edges in between them, and those edges may mean different things depending on the context. For example, here have transport data, so you have rail links, roads which connect cities, and you might have movement across those cities, and at the nodes you might observe some sort of time series at regular intervals, and you want to try and get a handle on what's going on, what's driving that process across time and across the network. As I said, computer security and computer networks is a hot topic, and so a lot of these problems can be applied to this sort of context. And thirdly, everyone seems to use social media these days. You have connections between people as to common friends, how many likes you have of their pages or whatever. And there's a lot of interest these days in trying to handle these big data sets across time and across these big networks. So the type of data I'll be talking about today as a summary is time series observed on the network, and typically we're talking about large networks. And this point is slightly different here. So a network can have a natural network associated to it, whether it's physical, like the transport data, or can be constructed. Now, the examples that I'm going to use in this talk are examples of how you can construct a network on these time series in general. And it's trying to get a handle on the time series as a multivariate time series, but you know there's some added structure there so that you want to try and use to help you in the analysis side of things. And lastly, because we're talking about large networks, what we want to do is find ways of analyzing these large network time series. And for the purposes of this talk, we're going to be talking about forecasting, but at the end I'll talk a bit possibly about other avenues, other analysis tasks that you might want to do. So that's the general setup. So what type of examples am I going to use for this talk? So the first toy example is about cases of mumps, which is a disease that you normally have as a child across counties. So there's some degree of aggregation going on here, so all you know is the number of mumps cases per county, and this happens a lot in terms of the statistics that are collected across the UK, different time series obviously, but this level of aggregation happens a lot. And so this is obviously week 1 and week 52, so over a year the dynamics of that process might change from week to week. And there are 47 counties in this particular example. What does this data look like in terms of structure. This is a correlation plot looking at the time series and then looking at cross correlations between those as sets of data. And so the high extreme ends of the correlation in green and this dirty brown here, you get lots of structure in terms of one county compared with another county. And across time, you can see that there's some sort of geographic dependency going on here. So, for example, Somerset and Avon, they're fairly close to each other, and so you expect that the dynamics of a process over time, so this is a spatial type measure, and over time there's also dependence there as well. So there's this complex structured data, and we're trying to analyze this over time and location. As a second example, Guy talked about this a little bit on Monday. There's a network of weather stations across the UK which measure atmospheric time series and energy time series, and so this is a plot of these weather stations across the UK, or rather England and Wales, and it measures wind speed over knots, hourly or daily. And so in this particular toy example, we've got 102 weather stations, and this is 721 records, so hourly over the course of a few years. I should say that the previous example was given to us by the Health Agency, and this data is from the BADC, which is data archive for UK Met Office and other agencies. So again, what does this data look like? There's correlation in time, so autocorrelation quite a lot, and looking at a lagged cross-correlation, there's also dependence across sites on this network of weather stations. And so again, we're trying to find some way of using all of this data, but also the spatial aspect of this time series object. Okay, so the title of this talk is to do with networks, and you might notice that both of these months and the wind speed data don't have an actual network in terms of nodes and edges. So we're going to construct one, and so there are many different ways of doing this, but I'm going to give a couple of examples of how we do that and what it means later on. So we can use, in terms of the county data, we can use borders between counties to link the data at a particular county. And from the weather station network, we can actually use geographic distance in terms of longitude and latitude to link these sites. And how we're going to do this in the example that I'm going to show you is using a minimal spanning tree. That's basically creating a graph out of some nodes and distances in a way that connects all of the nodes in the network, but in a simple way. Okay, so there are other ways to create these networks. As I said, transport corridors, rail networks. Guy, in one of his papers, did some analysis of rail delayed network data. You can use your friends and followers on Twitter or Facebook or whatever. And academic collaborations. So, for example, I collaborate with Guy. I might have a number of papers with Guy, which gives you some sort of strength of collaboration, and vice versa. So you can get some sort of idea about how strong connection you are across the network but you can create these sorts of things. Okay, so for the example of the county data, this is uses county towns, so municipal county towns, and looking at connections across county borders, so you get an idea, and that vaguely looks like the UK. And for the weather station network, this is a minimal spanning tree, so again, looks vaguely like England and Wales, but it's connected in a slightly different way. So it's a simple network, but which connects all of the dots, basically. And we have an idea of geographic distance between these points. So the earlier motivation for this is that we typically, for high dimensional time series across networks, the complex structure is quite evident. We have structure over time as well as over the network itself. And there's possible redundancy in the system. What I mean by that is, because we've got all this dependence, when we come to analyzing this data, we need to take into account this correlation across time and across the network, but perhaps we don't need to do that fully. And what can we do beforehand to simplify the analysis problem? And so, can we capture the network structure, and can we reduce the dimension of the analysis problem under question? So we might be talking about forecasting in this context, but spectral estimation or change points or something like that. And do we have to take into account all of the nodes in the network? How we're going to do this is using a transform, a wavelet-like lifting transform, which will convert our time series on the network to a simpler time series, and then you do your analysis on that simpler time series. And how we're going to do that is with lifting schemes, and I'll give a brief introduction to what lifting is all about in a conceptual way. So, lifting schemes were introduced in the mid-90s by Wim Swalband at Bell Labs, and it's all about doing wavelet-like transforms on complex data domains, and in this case on a network or irregular data in general. And it's useful for many different things. We've done some work in the area, but for the purposes of this talk, what we're going to use are the decorrelation properties of wavelet-like transforms, and in particular lifting. And we've done some work recently related to this in time series, where we've shown that lifting has really quite powerful decorrelation properties for time series. And it's these kinds of ideas, asymptotic decorrelation, that we're going to use today. Because we can do this transform on network data, the network structure is automatically taken into account. And a key thing for what I'm going to talk about later is the inversibility of these transforms. So they're computationally fast. You get an idea of what's going on in this data domain, and you can account for this network structure. Okay, so this is a very brief overview of the network lifting scheme that we're going to use, and there's mathematical theory behind it, but it's a very computationally simple idea. Say this is a part of our network. We've got nodes 1, 2, 3, 4, and 5, and the 2, 3, 7, 5, and 4 represent data on that particular node of the network, and 4, 4, 3, and 6 represent the weights of that link, so how strong the dependence could be between 2 and 3. So in terms of the data that we're talking about, it's physical distance, or some idea of physical distance, but say that could be 4 joint papers or something like that. So we pick a node and then use the surrounding values on the network to predict the one that you're lifting. And so we do this by taking a linear combination of these function values according to the weights on the edges. So you get a linear combination of these function values, and the detail coefficient of what you want to store in memory is just the difference between the original function value here and the predicted one. So it encapsulates some sort of local difference, local variation in the network at that time. We remove the point, reconnect the network, and update these function values according to the weights that were associated to the connection before we removed the point. So this was 2, I think, before, so it gets a portion of the function that was lost by doing this local differencing. So this is an updating of the network as well as the local neighborhood of that removed point. And we repeat it, so we pick a point, do this lifting, local linear combinations, encode the difference, go somewhere else in the network, do it again, do it again, do it again. And so once you do all of this across the network, then you have transformed your original data X into some other encoded time series, data, which has compressed it in some way. And because it's a linear transform, we can represent it by this matrix W. So if we were to change the data, then we could still do this matrix transform and matrix multiplication and do this transform. So in this sense, the matrix W is only dependent on the network structure that you have to begin with. And that's quite important. So that's a brief overview of lifting. As I said, it's computationally simple. It transforms your data into some other data across the network, but in a compressed way.
Does it matter which nodes you start with? Is it sensitive to?
I'll come on to that later. Yeah.
Another one, please. When you do the correlation, so you're looking at residuals. If you're looking in the, for example, if you have a change point problem, and you are looking for change in the mean, it will work, of course. But what happens if you're looking at the correlation functions in spectral characteristics? That it will just, remove all useful information.
Yeah. Well, this is the point. So I'll come on to this.
Not always works.
Yeah. So yeah, you've got this transform across the network, and so how are we going to use this for a network time series? Is fix time point 1, do your network lifting across the network, encapsulate that data, move on to time point 2, do the same thing, and so on and so forth up to the end of your time series. So you've done the same transform across the network, but just starting off with different data. And so now viewing this across time, so we've transformed the data across time and across the network into something else. Now viewing it across time, we've got these detail coefficient series, so these wavelet coefficient series that we can look at now across time. And typically with these wavelet-like transforms, you also get 1 or 2 scaling coefficients which represent the local mean of the signal. So you get the same dimension of the time series that you started off with, but what is this new time series object? Well, as I said, the transform is independent of the data in some sense. It only depends on the network structure you have to begin with. And what's key here is that the resulting time series is sparse. So what does this sparsity give us? Well, now looking across time, so we've only done something in the network direction, okay? But now looking across time, we get rid of all of the cross-correlation between nodes, okay, which is quite powerful. We haven't actually tried to do anything across time. We're only trying to do something, doing our network lifting across the network, but we can pretty much get rid of the cross-correlation here and a lot of the auto-correlation in the time series. Again, for the wind time series, you've got a lot of structure beforehand, and then the cross-correlation goes, and we got a lot of the autocorrelation has also gone. So, as you said, it's quite a it destroys all of the structure in the time series, but that's essentially what we're looking for, because what we can do here is now look at the time series and see actually what's going on. We've reduced the correlation a lot in time as well, so a lot of these time series transform to white noise. Okay, so you start off with something which is quite high dependent structure, and you get something which is white noise, and you get some other nodes which aren't. So what can we do here? So we've got rid of the autocorrelation here, and so we can model the remaining non-white noise as some low order armor or something else as appropriate, but the time series that are white noise we know how to deal with quite well. And so what does this mean in terms of the mumps data? We've got a high proportion of these things coming out as white noise, whereas before they were highly correlated time series. So you may think, oh, what's good about that? Well, the cross-correlation disappearing means that we don't, in our analysis side of things, we don't have to take this into account in the transform domain. We just treat everything separately, analyze it as you would normally as a univariate time series, and then invert it back to the original domain. So in terms of forecasting, what you do is perform this network lifting procedure, get rid of the cross-correlation and a lot of the autocorrelation. The scaling coefficients we transform, we can extrapolate forward normally. The white noise processes, we know how to deal with that, so we just use a null prediction forward, whatever the mean of the Gaussian process is. And for the remaining ones, you use your favorite forecasting method of choice. And then we, as I said, we invert the series back into the time domain to see what's going on. So you're simplifying your whole time series, doing whatever forecasting you want, and then inverting it back to get your time domain forecasts. So it's all very well. What does that actually do? So it's a bit hard to see here, but this is a plot of the percentage improvement from doing time domain forecasts was ignoring any correlation structure versus doing our lifting transform and then forecasting there. So this is using, I can't remember what forecasting it was, but why I wanted to show this was that there's a difference in where you get the relative improvements, and so it'd be interesting to see about why you get improvements at a lot of improvement at some nodes rather than the others. And I didn't want to make any massive claims, big claims here, because there's no simulation studies or whatever, but all the examples I've looked at, there's quite a lot of improvement rather than, so you're using the same forecasting method but just want one time in the time domain and once in the transform domain. And as the question from Sophia was, what does it matter what node you start off with and the ordering? Well, it does, but there is a way of choosing this ordering. But if you ignore that and just randomly choose and sort of do your forecasting as a bootstrapping type method, then you can aggregate the forecasting, and you can get a lot of more improvement than doing it once. So you can take that into account as well. And there's obviously the application dependent. You might want to choose your ordering in a particular way. So that's basic overview of the initial ideas that we're thinking about at the moment. So the preliminary results of this are encouraging, meaning that all of the examples, all of the highly structured network data, whether it's constructing the network yourself or having a physical network there, it seems to perform quite well. And we're not saying that we're coming up with necessarily a new forecasting method. We're saying come with your own forecasting method and shove it into this pre-processing and post-processing transform. And the idea is based on just simplifying the time series and using analysis in the transform domain. Obviously, there's some open questions there. How do you choose your network, whether it's minimal spanning trees or some other physical thing that you want to use? And there are other things that you can actually do with this, and it would be interesting to look at other analysis tasks as well as forecasting. And I'll stop there. Thanks.
This decorrelation across different nodes is what you intended. This whitening each series is kind of not intended because your method didn't look into this dynamic structure when you do the lifting.
Yeah.
Is that right?
So you're doing the decorrelation. You're lifting or wavelet transforms decorrelate. We know this, and so you were doing this across the network.
Yeah.
We're not wanting necessarily to do it across time, but when I say that here, optimal lifting strategies, I mean it's a kind of nice byproduct that you get this white noise effect going on. But I've been thinking about other ways to actually force it to get to white noise.
Yeah, this is my next question. You can do it kind of dynamical way.
Yeah.
Looking at the neighbor, also look at the negative value.
Yeah.
And you have sort of white on each series, also decorrelate across different series.
Yeah.
But if this.
Yeah.
I have another question about the lifting. So you actually do a different lifting transform at each time point?
So you're doing the same lifting at time point 1 as time point 2 or 56 or whatever.
Okay, I misunderstood that.
But yeah, adaptive transforms, you could conceivably do different ones, but trying to look at that as a time series is a nightmare. Right?
Okay, can we thank Matt again?